Today we learn about minimal submanifolds and more specifically about minimal surfaces. Let's start. Let's consider the simplest case. Consider R2, just a flat two-dimensional plane, right? And suppose we have 2 points in R2. So let A and B be 2 points in R2. What is the shortest path from A to B? Well, we know the answer to this question. It's just the straight line connecting them, the straight segment connecting them. It's shorter than any other curved path from A to B. The main question of this section is generalizing this problem to higher dimensions and trying to answer kind of a similar question. So let's start with the next kind of interesting but simple example. Think about R3. Suppose we have a circle inside R3. Suppose we have like a perfect circle with radius 1 sitting on the floor in R3, right? Think about surfaces inside R3 with boundary being this circle. Which one has the least area? Think about the solid disk, right? The two-dimensional disk. The boundary is exactly this circle. This disk has the least area among all surfaces with boundary being this circle. So for instance, think about this red cap, like a two-dimensional cap with boundary being the same circle, the red one. It's a surface with the same boundary, right? But the area of this blue disk is less than the area of this red cap, right? So it's kind of intuitive that the disk has the least area among all surfaces with boundary being this circle. The point is that proving this is not very hard, but if we were to look at a more generic kind of complicated curve inside R3 instead of circle, this would have been a harder question. So rather than starting with a circle, suppose we have a curve, a one-dimensional curve in R3, just a complicated thing goes around right anywhere in R3, and I'm looking for the surface. Let's say we denote this curve with sigma. I'm looking for a surface which boundary is exactly this curve, like this blue disk, let's say. It's topologically a disk, although it's curved. Let's denote it with S. So the boundary of S is sigma, but S has the least area among all surfaces which their boundary is this one-dimensional curve, sigma. So how can I find that? How can I find this surface S with the least area? Right. This is exactly like higher dimensional version of having the shortest path. There we were looking the kind of in some sense smallest one-dimensional object with given boundary. Here we are looking for in some sense for the smallest two-dimensional object. So this kind of happens naturally in nature. If you pick like a wire and soak it into a bubble or soap solution, you get these kind of soap films, which are like these surfaces. So here, look at this metal wire that plays the role of the sigma for us, right? And you dip that into some soap solution. And then when you bring it out, there is like a very, very thin film, very thin surface of soap, denoting it with S. This is exactly the surface which has or almost the surface, which has this least area with that given boundary. This is an example of something called minimal surface, right? Here on the right side, we have another picture. Here you see the boundary sigma, the curve is not even connected, right? But even if you try that, you get a surface S, which again has the least area, has the boundary being these disconnected components. And yeah, it has the least area among all surfaces with that given boundary inside R3. I found these two pictures on internet. It's a good thing for you to try to search more just to see more examples. Also, you can try this at home. It's a good experiment. You can try to construct these minimal surfaces. Okay. Now, let's see how we can think about this mathematically. Can we describe these surfaces using an equation, or do we have a mathematical way to describe these, right? For instance, for straight lines or more complicated case for geodesics in Riemannian manifolds, we had kind of an equation, right? Do we have such a thing for these surfaces with least area? Okay. One way to set it up is in so-called graphical context. Suppose U is a domain in R3. So it's kind of like an open subset in, sorry, a domain in R2. So it's like an open subset in R2 with its boundary. So suppose R2 is on the floor, and then there's an extra third dimension. Together they form R3. U is that solid region inside R2, just not just the boundary, but with the interior. If you think about U times R, it's just like translating U in the third dimension, right? So this is something called cylinder in math. So it would look like this. U times R would be a subset of R3, which is, as I said, just the result of translating U in the third dimension. So even if U is not a perfect disk, we call this a cylinder in math. So no matter what shape U has, this kind of object resulted by translation is called a cylinder over U inside R3. Okay. Now, suppose we have this wire, this like one-dimensional boundary, sigma, in the boundary of this cylinder. So our cylinder is this solid object, right? This solid object has a boundary, has a, like the kind of outside shell. Suppose we have the wire going around this cylinder. So I'm just drawing a blue one. Let's say this blue curve is our wire, which is supposed to be, the boundary of our minimal surface. It's like the thing we dip into the kind of soap solution. And suppose it goes exactly around once. And when we project it to R2, there's just one point above each point in the boundary of U. I'm looking for a surface S which has the boundary sigma, so 1, the boundary of my surface is exactly this wire sigma. 2, S has the least area among all surfaces with this given boundary. Right, that's what I'm looking for. That's, loosely speaking, that's what I'm calling a minimal surface at this point. So S has mean area among all surfaces inside R3, with boundary being this blue curve. Intuitively, it might be something like this green surface, right? It's a surface, and it has the boundary, this blue thing, and has the mean area, right? So I'm kind of trying to understand what is the equation this surface should satisfy. I'm trying to look for some more rigorous mathematical kind of way of describing this surface S. So a good assumption, which kind of one can motivate later, is to think about S as graph of a function over U. So I like to think about S as a graph of a function over U. So I want to think S is graph of a function f from U to R. What does graph mean? Graph is a pair of points x and f of x, where x is in U and f of x is in R. So x, if it can be any point in U, f of x can be any point in R. Graph of f would be a subset of U times R, right? Because the first component is in U, the second component is R. U itself is in R2, so U times R is in R3. So I want to think about this green surface as a graph of a function over U. So if we project S downstairs to R2, it exactly projects to U, right? So I want to think about it as a graph of a function over U. So especially kind of loosely speaking, the idea is that rather than looking for what the surface S is, now I can try to find what the function F is so that its graph is the surface with the mean area and with boundary being this sigma, right? So we are looking for a function f from U to R where it sends the boundary of U exactly to this sigma And the graph of our function has the least area among all surfaces with boundary being sigma. So kind of the goal is that thinking about functions is kind of easier than thinking about surfaces inside R3. And we like to find a way to write this condition that f of boundary of u is sigma and graph of f has the mean area to work that out, to write it as an equation for f. Okay, great. Um, Also, the assumption that the boundary, the wire goes around exactly once and doesn't go back is important here because we want to think about this surface and also its boundary as graph of a function. So loosely speaking, the goal is to find a way to translate minimality condition having the mean area for graph of f. We want to translate that to an equation, to some partial differential equation, to some PDE for the function f. And then if you can do that, then you can hope maybe you can solve this equation. Maybe you can show this equation has a solution. And then you can find, or you would be able to describe that surface more explicitly. Okay, what is the equation we get for f? Let me first tell you what the equation is, and then I try to explain why that would be the equation. Suppose I have a function f from u to r, which sends the boundary of u to exactly that wire. And also it has the property that the graph of f has the mean area. So the area of the graph of f is less than area of any other surface. Let's denote any other surface with sigma. The area of graph of f is less than any other surface area of any other surface sigma if the boundary of that surface is exactly this wire small sigma. Okay, then f satisfies some PDE. What is that PDE? What is that equation which makes graph of f to be minimal? So the PDE is the following. Divergence of gradient of f over square root of 1 plus the norm of gradient of f squared, divergence of this quantity equals 0. So this is the PDE that f would satisfy if its graph is the so-called minimal surface, is the surface with the mean area. Okay, this is sometimes called minimal surface equation. Sometimes it's called the minimal graph equation, right? This is an essential equation for us. So take a look at this equation for a few seconds and try to absorb it. Okay, great. So I don't want to explicitly prove this, but I want to tell you a bit about just general idea why this equation appears. So where does this equation come from? Why do we get this equation if graph of f is minimal? Okay, let me kind of give you a short, brief idea why this is the thing. You see here we have our minimal surface. Suppose we have this function f, which its graph is the minimal surface, is the surface with the minimal area, right? With the boundary being sigma. What does it say? How can we translate this to a property about the function f? How can we translate this to a property or a PD for f? You see, when we look at the graph of f, when we look at the area, if it's minimal, it means the area is, as we mentioned, is less than area of any other surface, right? So it would be less than, in particular, area of any surface sigma inside u times r. So think about this cylinder. If we pick any other surface inside this solid cylinder with boundary being this blue curve, it would have a larger or equal area. Right. So for instance, another choice for sigma can be this pink surface. Let's say we have this other surface with boundary exactly the blue curve, but the area of this other surface is larger than the area of the green surface, the minimal surface, right? Now, we can pick a kind of special choice for sigma. Suppose G is another function defined on the same domain. G is another, say, smooth function from U to R, and suppose on the boundary of U, G is equal to F. So G also takes the boundary of U to this blue wire. So if I look at graph of G, it also would be a surface, and the boundary of graph of G is also this green wire. Because the graph of F is assumed to be minimal, area of graph of F should be less than or equal to area of graph of G, right? Because, well, the area of graph of F is supposed to be minimal among all surfaces. Graph of G is just another surface, right, with the given boundary condition. So here graph of G plays the role of any sigma, any surface sigma with the given boundary condition. Right. Okay. Now, I want to pick a very special choice for the function g. So rather than saying any g, I'm going to construct a very special g. How? Suppose I have a function eta from u to r, some smooth function, so that this function on the boundary is 0. So suppose eta is a function from u to r, and eta of x is 0 if x is in the boundary of u. So it's only non-zero in the interior region of U. It's 0 on the boundary of U, right? Now, for any real number t, positive, negative, or 0, if I look at the function f plus t times eta, it's a new function from U to R. It's a smooth function from U to R. What is the value of this function on the boundary of the U? So on boundary of U, if I look at this function f plus t eta, the eta part vanishes on the boundary. It's equal to 0. So on boundary, it is equal to U. Sorry, it's equal to f. So f plus t eta on the boundary of U is equal to f. So that's a valid choice for a function g, right? If I call f plus t eta, if I call the whole thing g, it's a function from U to R, and on the boundary it is equal to f. So the area of graph of f should be less than or equal to area of graph of f plus t eta, right? Again, because f plus t eta has the same boundary condition as f, so the boundary of the graph of f plus t eta is the same blue wire, and because f, the graph of f is the minimal surface, the area of that should be less. So it seems like we are defining a function from R to R, or R to R plus. Let's denote this function A. What is this function? For any t, for any real number t, I can define A of t to be the area of graph of f plus t eta. So for any real number t you give me, I look at the function f plus t eta, I look at its graph, I look at its area, right? When t is equal 0, we get a minimum for, or at least a local minimum, or maybe a global minimum of the function a. Because when t is equal to 0, a of 0 is area of graph of f, which is supposed to be the surface with mean area. If it's a minimum, it's also a critical point. So derivative of a with respect to t at t equals 0 should be 0, right? If t equals 0 is a minimum for a, the derivative of a at t equal to 0 must be equal to 0. So if you kind of rewrite this equation, we would get what we want. What is area of graph of a function f? I kind of stated as a lemma. This is a good calculus homework, I guess. When you have a function f, when you look at its graph, the area of the graph is integral of square root of 1 plus derivative of f, norm of derivative of f squared, square root of this whole thing over u dx dy. Okay, that's the area of graph of f. So in particular, area of graph of f plus t eta would be integral over u square root of 1 plus norm of gradient of f plus t gradient of eta squared dx dy. Okay, this is the area of graph of the function. Now, derivative of this quantity with respect to t should be 0. This is equal to a of t. Derivative of a of t with respect to t when t is equal to 0 should be 0. So we should write this equation. We should say, if I take derivative of this quantity with respect to t and let t be equal to 0, this must be 0 because t equals 0 is a minimum. And if you work this out, I leave this kind of computations to you. If you work this out, it simplifies to this equation, that divergence of gradient of f over square root of 1 plus gradient f squared equals 0. So that's where this equation, the minimal surface equation, comes from. We get the minimal surface equation. So this is the equation f would satisfy if its graph has the mean area with the given boundary condition. Okay, great. Okay, so a few points. So here we have a mean, and we said mean is a critical point. So derivative of a with respect to t is 0. But to be honest, this is the critical point equation, not necessarily minimum equation. So when f satisfies this equation, it simply means graph of f is a critical point of area function, not necessarily minimum. So is it really true? Do we really get a minimum for the area, or it might be a maximum, or it might be a critical point? The answer is that if the region U is convex in the sense that any 2 points you pick inside U, you connect them through a straight line, that segment would be inside U. Graph of F would be the honest minimum. It has the least area. It's a global minimizer of the area function. If U is not convex, so if the region we pick U in R2 is not convex in the sense that there are points which if you connect them, it does not fall exactly inside the region, then the graph of F would be only the local minimum. It's not the global minimum. So there might be some surfaces which have less area than the graph of F, but they might not fall inside the region U times R. So there might be graphs which go outside of this region with the given boundary condition and have area less than graph of F. So I just mentioned that kind of as a remark. I didn't prove this at this point. So also this extends to higher dimension. We took U as a subset of R2. We could pick some U domain inside some Rn. And we could think about maps from U to R. Again, the graph of this function f would be a subset of U times R, which is Rn plus 1. Now here, instead of area, it makes sense to think about n-dimensional volume of the graph of f. And then one might try to minimize volume of this submanifold. Right. So just like we wanted to minimize the length of curves and we got to geodesics, we wanted to minimize area of surfaces, we got to minimal surfaces. It makes sense in higher dimensions to look at the functions where their graph has the minimum volume. So volume, n-dimensional volume of graph of f, let's say, is less than n-dimensional volume graph of g for any function g which agrees with f on the boundary. So it's just like that wire we picked. Now this is a higher dimensional version of that. Again, f would satisfy the exactly same equation. So in fact, in our argument, we could extend anything to the n-dimensional space. So the graph of f is called a minimal submanifold here, rather than a minimal surface. It satisfies the exact same equation. Another point I want to mention is Bernstein-type theorems. This is quite important, in fact. We picked U to be a region in R2. What if U is the whole R2? Then there is no boundary anymore. Then there is no wire. What happens if we have a function from R2 to R, no boundary anymore, which satisfies the same equation, the minimal graph equation? Divergence of gradient of f over square root of 1 plus norm of gradient f squared equals 0. What happens then? Well, then it's not very hard to show. It's also not easy. I'm not going to prove it here. That f is a linear function. So f of any point x and y in R2 is ax plus by plus c for some constants abc. So the graph of f is just a flat plane, right? It's not curved at all. It's just a flat vector subspace or affine subspace. It's easy to see this linear function f satisfies the PD written there. The converse is hard, that any function satisfying this PD must be just a linear one. One can ask the same question in higher dimensions. What if I have a function f defined rather than from R2 to R, suppose it's defined from Rn plus minus 1 to R, and satisfies the minimal submanifold equation. So we learned graph of f is minimal if divergence of gradient f divided by this quantity equals 0. So it's minimal submanifold equation. Can we say the same thing? Can we say f again is linear? So this is the higher dimensional version of Bernstein theorem to say f is linear. But is it correct for any natural number n? Can we say in any dimension, if f satisfies this minimum submanifold equation, can we say f is linear? Is it correct? So it's correct if n is less than or equal to 8.